All right, so team one, the floor is yours. So go ahead and start your presentation.
Thank you. Good morning, and thank you all for being here today. Allie, Anna, Dave, and myself are excited to present the strategy that we've been working on for the empty lot redevelopment here in DC. This slide highlights some of the key topics we'll be discussing today in our presentation, and I'd like to note that each slide has slide numbers on the bottom, so if you have any questions at the end, we can refer back to the slide. Our project is the design of temporary homeless housing for the city of DC. There are many empty lot spaces throughout the city that are sitting unused between their purchase and development. So the end goal of our project was the utilization of this empty lot space for the benefit of the community. Our goal was to create a general or modular design that could be reused and implemented for multiple lots throughout the city. We chose to design this for our project after learning of the statistics regarding the homeless population in DC. As of June 2020, the population of homeless individuals in DC was 6,380. And this number doesn't include those who were displaced due to the COVID-19 pandemic. While there are a number of homeless shelters throughout the city, there are approximately 650 individuals that are unsheltered and living on the streets, in parks, or in other public areas. The limited number of beds in these shelters requires the need for a new means of providing shelter to these individuals. The goal with our project is to be able to provide modular housing for up to 80 people on an individual lot. Our solution is the design of a single unit with plumbing, heating, and air conditioning. Given the goals of our client, we wanted to design these units with a focus on cost effectiveness, increased livability for its users, and added aesthetic value to its area. We created a community of units that can be easily transported between vacant lots as needed, and again can provide shelter for up to 80 individuals. On the map of Ward 6 on the right, the red arrow points to the location that we've chosen to design the base of our project. On the slide, you can see images of this location from the previous map, which is located at 200 K Street Southeast in Navy Yard. On the slide are pictures of the site's current condition that were taken from our site visit last semester. We use this particular site to create a general site plan that could be easily modified to adapt to various lots. We also created our water analysis based on the resources available at the site, but again, it could be adapted to any given site. This slide depicts an overview of our site plan. Our site is surrounded by residential buildings, which are shown in black. The orange is representative of the individual housing units. Each of these units will include a bed, a desk, and a bathroom. The purple represents communal kitchen and dining units that will be accessible to all of the residents. The yellow represents the library and community space. These units will be open to both the residents as well as to the public and will contain access to computers and work areas as well as books that will be donated by the local community. Lastly, the green areas represent the community garden and the local park that are accessible to all members of the area.
Here we are showing the floor plan for each individual unit. Each typical unit has a 5-foot porch at the front that you enter through to get into the main living space. The bathroom and mechanical space is located in the back of the unit. This space will only be accessible to maintenance personnel if needed. On the next slide, you can see our two main sections taken through the unit. In the two main sections, you can see that our design includes the use of a clear story window. By utilizing a clear story window, we were able to provide our users with not only more privacy, but also much more natural daylighting into each unit. The clear story also allows us to place each unit closer together on the site, in turn allowing more total units to fit on the site. Finally, the clear story allows us to have the flexibility to connect units together if needed, much easier than if the units were placed on each side of the container homes. You will also notice that the units are elevated off the ground about 3 feet. This is done to protect the units from potential flooding and also allows us to not have to place additional concrete pads underneath each unit on the site. We will also be providing a percentage of the units to be designed with ramps to be ADA compliant. On the next slide, you can see a wall section that shows the typical assembly for each exterior wall of the container home. These units will be prefabricated and ready for use before arriving on site. The walls include 2x4 studs for framing, spray foam insulation, and then finished with gypsum wallboard on the interior. On the right, you can see a call out showing our roof assembly. You will also see here the clear story will require extra sealant and waterproofing to ensure thermal stability of the unit and also protect each from water damage. As you can see, we kept the design and assembly of each unit fairly simple in order to cut back on costs, as well as construction time for the units. On the next slide, you can see two elevations of the unit. This just gives you a sense of what the exterior of the units is going to look like and also gives general dimensions for each size of the unit. The next slide shows two interior views. We put these in to show the interior layout and also show how much light enters each unit through the clear story window. On the next slide, you can see that we ran structural analysis on our model using the SAP 2000 software. We use this to ensure that our design will be structurally stable. We assigned dead and live loads to represent gravity, wind, and snow loads. And here you can see our model after deformation. On the next slide, you'll see the final shear force diagrams with the results on the right-hand diagram. And on the next slide, you can see our moment diagram, again with the results on the right.
We performed a steady state pressure analysis using Bentley's Autocad system, and that was based on an assumed demand of about 1 shower, 4 toilet flushes, and 30 minutes of sink use a day with a safety factor of 2. And that was checking that all of the pipes reached the minimum pressure requirements provided by DC water guidelines, and they did, in fact, which you can see on the next slide. The pressures ranged from 68 to 73 PSI, which is more than enough, especially to account for that jump from the connection in the water main underground to the above ground pipes. And on the right, you can see the actual layout from Autocad showing that we're connecting to the water main on the east of the site. This is a closer look at the connection to the actual unit. It is very similar to an RV connection, also showing how the units will be stacked right next to each other and easily access the pipe connecting to the water main. This is showing the existing manholes on the site. We're looking to connect to the one on the southwest corner. And this is just a look at the sewage connection, how it can run in parallel to the potable water connection and connect the sewage down the line with that flexible pipe connection.
This slide shows the methods we're planning on using to provide electricity, heating, and cooling to each unit. Each unit will have a 100 amp service panel, which is more than enough to service the uses of an individual. This will also power the mini split system of heating and cooling seen on the right. These are ductless, eliminating the need for expensive and time-consuming duct installation and allowing for more individual comfort. Here you can see the breakdown of the cost to construct our facility. We factored in items such as the containers themselves, as well as materials and labor. And the important takeaway here is the final line showing that our project will cost a little over $1.2 million to start. But to minimize cost, we can reduce the number of units and encourage community donations, which you'll see more of later on. You can see that it will cost less than $400,000 every year to run and maintain, with the bulk of the cost going to the permanent staff we have on site to make sure things are safe and running smoothly. We'll be asking the DC community and possibly corporate sponsors for donations of items such as beds, toiletries, kitchen appliances, and laptops. And we're just really looking to minimize the cost to the individuals living in the actual facility. Here you can see a simple chart showing the time it will take to fully fabricate one unit. The major takeaways from our schedule are that one unit will take about a month to fully fabricate, but the strength of our system is in the transportation, where they can be easily loaded on to flatbed trucks and moved to the desired location. They'll be moved in groups to try to minimize transportation costs. So when about 10 of them are completed, they'll be moved over and the facility will grow over time. While the units are being built, we'll be getting the site ready. That means doing things such as setting up a pump, installing electrical systems, and configuring appliances, which we expect to take about 4 months. Like I said, it'll be moved in groups, and we'll need a crane at each site location. Thank you for taking the time to listen, and we'd be happy to answer any questions you have.
Great. So now from our outside guests, please feel free to ask questions.
I have a question I can start us off with.
Go ahead, Grace.
Yeah, so you mentioned that you wanted to minimize costs to residents. What's the approximate like monthly cost for residents, and how did you determine that?
David, do you want to answer that?
Oh, yeah, sure. Monthly cost to residents, we see it as kind of following a similar model to DCHS, I think is the acronym, where I think if residents give a certain percentage of their income, I don't think it really matters how much they make. I think it's just a certain percentage of their income being paid towards that, and shows that they have a certain level of stability that I think that qualifies them to live in this facility.
Thank you.
May I ask a question?
Yeah, go ahead, Arash.
So this is Arash from Civil and Environmental Engineering. So you talked about the structure analysis. I was wondering what loads did you consider on the structure?
So for our initial analysis, we assigned gravity loads, snow loads, and wind loads.
Got it.
All right, well, go ahead, Arash.
You know, so I have another quick question. So you showed the scheduling. It looked like basically the tasks come right after each other. Is there any reason for that? Is there any way to kind of do some of the tasks in parallel to, you know, allow the project to finish faster?
Yeah, absolutely. We were actually thinking of having an off-site facility that would fabricate the units that would probably work on, like I said, about 10 at a time, so that it would kind of have some overlap with the contractors actually building it, so that, you know, they could do one job on one unit and then move on to the next while somebody else worked on the previous unit. So that would create some overlap and probably save some time.
Got you.
Great. Do we have any other questions?
Hi, this is Dan Murphy. I just had, I guess, a question of, did you consider any sustainable features such as like rainwater capture, gray water use, solar panels as part of your project?
We did, but we didn't model them, so that's why we didn't include it. But we were looking to use rainwater catchment from the roofs of our system to water the community garden so that they could actually have some form of sustenance.
All right, well, thank you, Team 1. Let's give them a big round of applause. And we'll move to Team 2. If you could unshare your screen, Team 1. All right, go ahead, Team 2.
So good morning, everyone. Our design is a Federal Reserve Board Eccles rooftop terrace design. Our team is Matthew Cornelisi, Woody Choi, Raymond Molnar, and Garrett Boyd. So as a team, we have been working on the design of the rooftop terrace of the Eccles building for the Federal Reserve Board. The Eccles building is located on Constitution Avenue Northwest in between the Lincoln Memorial and World War II Memorial. The main dynamic for this design consists of developing a green roof infrastructure system that is sustainable and environmental friendly. The purpose of this project is to develop a social, relaxed location for the Federal Reserve Board members as well as guests. This rooftop has views of the nation capital's most breathtaking monuments and memorials. With this project came many challenges, including learning software such as Revit, SAP 2000, and GIFMod, as well as a fall prevention system to prevent any injuries and potential falls. It took us roughly 9 months to complete from start to finish this design. So our project agenda includes our location, project constraints, architectural solutions, iterative solutions with GIFMod, structural design with SAP 2000, final design with Revit, cost estimate, and sustainability. And it's just a map of where the Federal Reserve Board building is, Eccles building. So visual constraints are the first of the constraints put in consideration. The design of the terrace will be so that the occupants on the terrace, as well as any activity that will be going on, cannot be seen from Constitution Avenue. This is to maintain the architectural integrity of the historic building. Fall prevention is the next constraint to consider. We designed the roof so that there will be a 10-foot distance from the ledge of the building roof, complying with the 2018 IBC codes, and a 34-inch railing height to comply with OSHA safety codes. This can limit the amount of usable space on the roof to design our terrace. Capacity constraints is another constraint. Due to the current roof capacity, we have to make sure any additional live or dead loads we added in our terrace design fell within the available roof capacity. Routine maintenance is needed to keep the garden roof pristine and in good health. The three main areas of maintenance are watering, weeding, and plant care. We chose to use an extensive green design so that there would be little maintenance needed, and we chose plant species that do not need supplemental irrigation. According to the DC DOE Stormwater Management Guidebook, the roof should be inspected by a qualified professional twice a year during the growing season to look for leaks and drainage problems.
So looking at the architectural solutions, so here you see a visual of the SketchUp model. This includes a modern look as well as a rain garden, a regular garden, and has a recreational feel. It contains lounge chairs, picnic tables, ping pong tables, and also some TVs that are hung up. All the furniture will be resistant to the DC weather, so the rain, humidity, sometimes the snow, etc. And since we're designing both the east and the west side rooftops, we just went with the same design for both. So this is going to be the design for both. And then lastly, this is not the final design, but we wanted to show the progress that we made throughout the year. The final design was created in Revit, and then it'll be shown later in the presentation by Ray. So this is just like our preliminary design, just to show the progress that we made throughout the year.
So GIFMod is a program used for designing models for evaluation of performance of stormwater on green infrastructure. Our model represents a hydraulic model of a rooftop rain garden. Each colored block represents a component of a rain garden, such as collecting water, plants, growing medium, filtration, storage of drainage and water retention, a root barrier, water membrane, and groundwater. The water absorbed in the system will be used to replenish plants with natural rainwater. This model offers an approach to the rain garden system and how the water retention is controlled. As you can see, as our model, the data determined represents the conceptual mode of rain garden in GIFMod during the course of simulation from February 2020 through February 2021. The outputs we wanted were precipitation data, under drain and overflow rates, but overall GIFMod is used for the precipitation data and how much precipitation can pool in the rain garden.
So for the structural part of our project, we looked to actually model the building within SAP 2000. That was the software that we went with. And so here you can see kind of just a layout of the beams and columns in SAP 2000. And this is, again, the overall layout of what the building looks like. So just to get an idea. So the purpose of, to design the green roof terrace for the Federal Reserve building, we had to obviously calculate the load capacity of the existing structure in order to figure out what additional loads could be applied to the rooftop without exceeding the capacity of the building's structural elements. So with a building of this magnitude, the model seen above has to be broken up into simple frame sections. And this way, this allows us to size and design the building elements according to the loads acting on the 2D frames. So if you see this next slide, this is a screen capture of the first frame that I modeled, the first and second frames that we modeled in SAT 2000. This replicates a section of the building itself. So on the left, you see the dead loads acting on the interior frame. On the right, you see the live loads acting on the interior frame. So there's dead, live, snow loads, rain loads, and these are converted into distributed loads, so pound per feet, and these act on the frame members. On the right side of the picture, you can see the calculated dead loads again, and this is applied on each level. So you'll have the dead loads acting on the roof, on this third, fourth, second floor. The live loads, are also present on that right picture. So just going a little bit more into kind of explaining the scale that we have. So, well, first off, for the live loads, we used 30 pounds per feet squared, and for the roof, and then 70 pounds per feet squared on the other floors. And then for the snow load, we ended up going with 27.5 pounds per feet squared. And so on the you see that there's a colorful frame, and basically the way that works is there's a scale, and that scale is the demand to capacity ratio. So you see it goes from like that gray color to the red color, and the closer the DC ratio is to 1, which is the red section, the closer the failure your system is. So you don't want the highlighted color of your beam to be equal to that red color, because that means that your beam will experience failure, or it will experience it will start to bend or fail. And so the sweet spot for each beam and each column is around that 0.9 area on the scale, because this was where the cost of materials can be minimized while still maintaining the system's structural integrity. So if your DC ratio is far below 1, in other words, if the colors are very close to the bottom, then it's obviously it's kind of overbuilt, where it's over designed. Sorry, that's the right way to put it, where money is kind of being wasted on heavier duty material when unnecessary. So we used S5 by 10 columns and S3 times 5.7 beams, as you can see for the different columns and beams. But basically the idea is, we run through different iterations, and with these dead loads and these live loads calculated, the main thing was just to make sure that the beams fell under that red scale, so under that 1 demand to capacity ratio. So these are just the portal frames again, and also these were the interior frames. So the exterior frames, portal frames, and the interior portal frames are going to be slightly different, because on the exterior you're going to have cladding and different things acting on the exterior portal frames. So you get the model with an interior frame that's further, as it says, in the interior of the building, and then an exterior portal frame, which can be seen here. So going into our final design, we went into Revit. So originally we were using SketchUp, as Garrett said, but we wanted to kind of move the project into Revit, because Revit, it's a great program, you can do a lot with it. Unfortunately, we didn't have Enscape, so we wanted to throw that into Enscape, but I accidentally downloaded the 2022 version, and I didn't have the 2022 version of the Enscape, so that was unfortunate. But here you can see just kind of an overall view. The gray building, that the main focus wasn't on the actual building. The focus again was on the green roof, but we wanted to throw in the building just so that you can kind of get an idea of where the location is, and how the green roof kind of fits into the overall building. And those glass curtain walls and ceilings are conceptual right now. So in part of the concepts of the new additions to the Federal Reserve building, they have an idea of kind of adding these glass curtain walls. So we wanted to throw those in there too, to make it look pretty cool. So this is just kind of a view from the back. Top. So this is kind of a zoomed in view of the top, so you can see kind of the layout of the roof in Revit. So you see it's kind of surrounded by some bushes and soil. We have a patio space with pavers, and we have some tables, a lot of lounge chairs and couches. We have an upper deck which is raised about it's elevated about a foot above the patio. So when you go into some different views, you'll be able to see that a little bit better. But on that kind of that dark patio space, you'll see some ping pong tables and some lounge chairs, also a corner couch. So just a very relaxed area where you can sit down and have conversations with coworkers and relax a little bit. You know, kind of looking south for that picture, you see green area where there's some different gardens that we have. You see that kind of path, that paver path that leads to that shed, which in this view it's very hard to see, but there's a shed with some solar panels on the top, which you see in those series of arranged squares. Those are supposed to be solar panels, but the render came out weird for some reason. But yeah, we have some lounge chair, we have some other lounge seating, some lawn chairs, as I should say, and some grass and gardens. So this is kind of just the overall look that we ended up going with for our final design. So here's another view. Again, you can kind of see now there's railings that we have in there. There's glass railings, and the railings are set back about 5 feet. There's a 5-foot buffer between the wall and the glass railings, and there's just grass that's in between. We just figured we'd put in, you know, add some more green space, or it's good for the whole system. So you see the elevated patio, the elevated kind of deck, I guess you could call it, above the patio. It's about a foot above again. And again, just another kind of a cool area just to give some separation between the patio space, the garden, and the grass, and then, you know, the patio. So I thought it looked pretty cool. And you can kind of see the shed now. The shed is that structure on the left that kind of pops out. And for the shed, we figured, you know, for any cushions that we don't want to leave out through the winter, we can put, you know, all those cushions within the shed and store anything that wants to be stored in there. Also, the solar panels, we were looking to use the electricity to power those TVs on the wall. You can see there's some outdoor TVs that are posted on the wall. And so that was just kind of an idea we had, just to throw those on there for toss on different sports games or events or whatever. But the solar panel, the electricity generated, can power those TVs and any outlets we have on the rooftop. This is just another rendered view, kind of zoomed in a little bit. You can kind of get a better idea of each component, what it looks like. Again, on the left, you'll see those lawn chairs, those gray lawn chairs. Kind of hard to see from this angle, but you'll see some of those. And then you can just see the patio furniture that we chose. So again, this is just another view of our renderings. This is just a view kind of as you walk out onto the patio. So this render got stretched a little bit, so it looks like the pavers are rectangular shaped, and it looks like everything's kind of stretched out. But again, it's more, you have square pavers and everything's fairly square, but it's just the, you know, how the render came out. But kind of just, if you walk out on the patio, this is a view a little bit from above, just looking down, so you can see again ping pong tables. And then it's supposed to be a relaxed space, but a recreational space. Kind of a view looking into the gardens and the green space. Again, you can see that kind of that 5-foot buffer of grass in front of the railing, and then you see those bushes and the grass, and you can kind of see the shed a little bit. There's lawn chairs to the right and a view into the patio space. So these were just some unrendered drawings or whatever that we had in Revit. So overall, that was the kind of the final design that we went with. Again, we wanted to move it from SketchUp to Revit. We felt like it would be a good way to kind of finalize our thoughts. So we're moving to the cost estimate.
So then looking at the cost estimate. So as you can see, it's broken down into 4 sections. So we got the item, the quantity, the cost, and then the total cost. So the total cost was made up of the quantity times the cost, because the cost is per each item or each square foot or footage in this case. So yeah, it was a total of about $1.27 million. So that's for both rooftops. So what I did for the cost estimate was I did it for both sides. So for instance, the roof pavers was 6,200 square feet. So I broke that down into, that's for both. So it'd be 3,100 for each, for like the east side rooftop, and then 3,100 for the west side. So in total is about 1.27 million. So it was roughly about 635,000 for each rooftop.
For the sustainability, we ended up choosing the Hydrotech extensive garden roof assembly. This will reduce urban heat island effect. Ultimately, this will also reduce the dependence on and the cost of municipal water services, which reduces tax as stormwater runoff fees from the District Department of Energy and Environment, also known as the DOEE. The Hydrotech extensive garden roof assembly offers the opportunity and have proved to double or even triple the life expectancy of your rooftop. The barrier of greenery helps protect the waterproof membrane underneath and ensures the rooftop's life expectancy, which will last well for decades. For choosing sustainable plants is also a part of the design as well. Height and width of the plants, sunlight that plants require, well-drained soil, pest resistance, drought tolerance, hardiness in cold temperature seasons for the survival in the cold and winter temperatures, soil type, and the pH level conducive to good growth for the plants, and the longevity of the plants are all taken into account. So the 3 plants that will be used are lavender, which is a herb to place along pathways or near outdoor seating areas so you can experience the pleasant fragrance. The second one is the blue fescue, which requires a few maintenance needs. And the third one will be the gold flame, which is a great way to attract hummingbirds and butterflies to the rooftop garden. That brings us to the end of the presentation. We would like to thank Jason, Grace, and Maria for their assistance to our green roof project. We would also like to thank Jeff, Chris, Skip, and Stephen from the Federal Reserve Board to allow us the opportunity to work with them. If anyone has any questions, we will be happy to open up the discussion. Thank you.
Great, thanks, Team 2. Let's ask any questions from our guests.
This is Scott Stewart with SK&A Structural Engineers. This first, I'd say, it's a great project. It's very representative of evaluations and adaptive reuse projects that we see on buildings in the district. So I think it's a very good experience from that perspective. With regard to the structural analysis, I guess, Ray, that was you that presented that. Oftentimes when we get into these types of projects, the most critical components are the existing roof slab or roof framing. Did you evaluate those individual components, and what did you find there?
Sure. So the original, again, that was the original idea, was we were going to be able to try to run an existing analysis, or an analysis on the existing structure, like you just said, because obviously that's what's there. You know, that's what we have, that's what we're working with. So we, given the limited resources that we had in terms of access to those like existing plans for the column layout and the beam layout, we weren't able to actually figure out every column and every beam that was there, just because we didn't have necessarily access during the time we were running this analysis. So what we ended up just doing was we kind of just assumed we were starting from scratch. And so we weren't really able to run that analysis on the existing beam elements. I know we talked to some people and they mentioned that that's one of the problems that they're having, is that the existing building elements actually aren't able to support the dead loads, live loads, whatever the load capacities of the proposed roof. So they're going to have to add, support through, whatever structural elements they have to add. But again, we didn't get to run that analysis on the existing structure. We kind of just had to start from scratch per se, and that's how we approached it.
Okay. All right. Thank you.
Thank you.
This is Arash Parham with Clark. And good job. It's a really interesting project. So back to that structural analysis. One thing that I noticed is that looked like the second floor or the second level of columns had more stress than the bottom layer, or the lowest level. Do you know what is contributing to that, or any idea?
Go back to it.
Maybe I,
Was it this one? Or?
yeah, this one, right.
Yeah, so there's more stress.
So you see that the second floor is
Oh yeah,
orange versus.
yeah, I see that. Yeah, that was something that was interesting too, because I'm not, because when you ran like the analysis and you ran, and you could see the deformation of the structure, it looked fairly normal in the sense that, you know, everything seemed to be in right terms in the program, and it looked to deform, you know, the way that it naturally would. It didn't seem to be, anything seemed to be out of, you know, anything was out of whack or anything like that. So I did notice that, how obviously you can see those S5 by 10s have more stress on them. I'm not sure like why that came out the way it did, because, you know, there's larger dead loads and there's larger loads acting, you know, on the top. So you'd think that there'd be more stress there. I don't know if it was just the combination of those loads from the top. I think it was the combination of those loads on the top and the weight of those additional floors on top of those columns, those particular columns. It was fairly close to one, as you could say. I mean, ultimately that was the sweet spot. Ideally, we would have all those beams and columns in that orange region, because that's where you optimize your costs. You know, you don't overpay for oversized, or, you know, over heavy duty beams. You know what I mean? So ideally, every beam and column would be in that orange region. But I think, again, the reason why it's in sort of that orange region is because for that specific column, the additional loads from above are kind of pushing that column to its you know, max. I mean, didn't exactly reach that one for the DC capacity, but I think that's kind of where that was coming from. But again, it's interesting because the S5 by 10 below it has, you know, it seems like it's lower, so it's handling the loads better than the columns above it. So that is interesting.
Yeah.
I'm not exactly
Yeah, as I said, I mean, it's one frame in a larger building, so that in a larger frame. So, and then the column sizes, it's something that you guys assumed, right? It's not something that based on the actual, correct?
Yeah, we
Okay.
didn't. Those weren't the actual column sizes. Again, we didn't necessarily have access to them during the time we were doing.
Right.
So.
Yeah, we had a little more difficulty with as-built and access because of COVID than expected.
Understood. No, that's and also it's also restricted building as well. And then one more thing about the roof, the cost estimate that you had. Did you guys assume anything for cost of you know, electric, water service or anything on the roof? I didn't see that. Or what are the thoughts there, or lighting for that matter?
Yeah, so for that section, we didn't really get into that as much. We more did like the materials, and then looking at the demolition, the labor, overhead, and the permit fees. So we didn't really get into that as much, but yeah, we'll definitely in the future we'll do that if we were to do this project. Yeah.
Right. You can just throw like a allowance there. I mean, if that would always just to make sure that shows that you thought about that.
Yeah. Okay.
Good job.
Thank
All right, so thanks for the questions. We'll for time we'll move to team 3. We're a little bit behind schedule, which is okay, but we'll try to speed up just a little bit. Team 3, can you share your screen?
Is it coming through?
Not yet.
Okay. Janelle or Eric or Ken's, would one of you be able to try? It's not letting me do it.
Yeah, I can try. Can everyone see my screen?
Yes, we do.
Okay. Sorry about that. Okay. Hi, everyone. We are presenting to you our multi-use golf and gym recreational building by Project Team Jesk. That's Janelle, Eric, Sean, and Ken's. And our client is the City of Bowie. So the project is located in the City of Bowie, Maryland, and it's located on the existing Bowie Golf Course. The building design features a partially submerged foundation with the first floor made of concrete and a second floor made of prefabricated metal. A golf cart storage facility is located on the ground floor for easy access, and the gym amenities are located on the second floor of the building. So we suspect that the daily users are going to be around 200 people per day on the weekdays and up to 500 people per day on the weekends. The budget given to us by the City of Bowie is 6 to 8 million. And gender neutral bathrooms are really emphasized in the building by the client. And the building takes advantage of the land slope, allowing for a partially underground foundation and first floor. So for our first design iteration, we use SAP 2000. So our client, the City of Bowie, actually wants our building to be made of pre-engineered metal. And fortunately, the requirements of the design allow us to do that. So here we have a partially concrete foundation, meaning that some of the panels on the exterior of the bottom floor are CMU. All the remaining panels are part of the glass facade. Besides that, both floors consist of precast concrete slabs, and all of the columns and beams of the building are made of steel. For this iteration, we went with a flat roof as opposed to a sloped roof, which is different than what we use for our final design. And these numbers here are some wind pressure coefficients that we use when we applied loads for the structural analysis. I also wanted to mention that since it's a flat roof, an idea could be to turn it into a unique golf viewing area since it overlooks the golf course, but it might also create an issue if a gutter is not properly installed, since rain and snow loads can cause unnecessary stress on the building, and runoff has to go into open piping systems.
So looking at our concrete iteration, we chose to focus on the lower level here, as again, it's going to sit partially underground. This utilizes a mix of slab pours, columns for the vertical loads, and CMU block walls for the lateral earth loads. A majority of the space is going to be saved for cart storage and maintenance, with some spatial considerations for golf admin purposes. And we'll take a look at a layout breakdown on the next slide. Can you go back real quick? So looking at that render in the bottom right, the green is for areas of minimal stress or no stress. The blue is areas of stress acting upward, and red acting downward, which focuses a lot in the corners. This was developed using SkySieve, which is an online cloud-based software useful for concrete design, and it focuses on ACI code 318-19. Again, there's not going to be any interior elevator, so essentially this is going to be two separate buildings on top of each other with all entries at grade. And to accommodate this, we will have ADA compliant ramps for wheelchair or walker users. Next slide. And then here's that breakdown of the space on the bottom floor. That area in the blue there is that whole cart storage and maintenance area. And then on the left, we have some considerations for bathrooms, concessions, and an area to pay greens fees. And once golfers are satisfied with that, they can go to the top left in the red, get a cart, and drive out to T1.
So for the timber design iteration, the team considered the use of a timber frame for the second floor of the multi-use building, and will consider a concrete slab for the lower level, which is designed for the cart storage. Timber was chosen as the main framing of the second floor because of its durability, ease of use, and ductility with respect to the function of the building. Another reason for why timber was advantageous in this project is because timber roof framing is able to achieve long spans given the assumed dimensions of the building. The ground floor was used as a storage for the golf carts and was modeled with concrete walls with openings along the x-axis of the structure as shown in this rendered model of just the columns and framing. The design of the second floor includes wall panels with openings instead of the initial design of a glass curtain in order to avoid side swaying of the structure. The model was then simulated and analyzed using the 2018 IBC Strength Code. Next slide, please. So the structural analysis of the multi-use building will be using RESA 3D software for both the concrete and timber materials. The color grade, which corresponds to green, means the member passed in deflection. A value lower than 1 is acceptable. The color red for a highlighted member indicates that the member failed, which refers to a value of 1. The model passed deflection for the walls and framing for both the concrete and timber material with a value between 0.01 and -0.2.
Here are some of the constraints we faced while doing the project. One was trying to stay in budget, which is between $6 to $8 million. Time, making sure our designs were done on time. The most challenging constraint we faced was the site condition. Before any excavation can take place, the site must be leveled. And with our site, it had multiple dips around the area and like elevation slightly leans towards the west side of the place. And the end user as well, we were trying to make sure we like estimate the correct amount of like users that will be in the building since the facility is going to be like weather and event dependent. So it was hard to approximate how many people are going to be there.
So for the codes and standards, the building codes we used were in accordance with the City of Bowie. The codes applied for the wood building iteration were based on the IBC 2018 Strength Code. The codes applied for the concrete sections of the project were referenced from ACI Code 318-19. The final design of the project will refer to the AISC Steel Construction Manual 15th edition. So for the architectural solution, the team has planned to create a mixed-use building with a 2-floor design, having the basketball court on one floor and the golf amenities on a different floor, which helps separate the visitors and makes it easier for the parties to carry out their individual events. Our steel frame structure will support a large glass panel facade, allowing for large amounts of natural light to enter the inside of the building, which is shown in this initial rendered model. The look of transparency is a property that both the City of Bowie and our project team would like to obtain.
Here's a look at the breakdown of our budget. Again, the number given by the city was between 6 and 8 million. This is down from a original $13 million recommendation given by a firm for a full brand new all-inclusive clubhouse, which they were trying to avoid. They wanted a space that's a little more open to the public. We chose to use the master format for a breakdown of materials, and there's also breakdowns for the labor, equipment, and some other miscellaneous prices. A special condition, again, we're going to be saving on elevators as there will not be a necessity to have them in the building. However, we're probably going to be making up that cost in excavation and site prep. And then on the next slide, we'll look at totals. So the total number we came to was just shy of 6 million, 5.6. This allows for some overhead for anything missed or changes in the future, some salaries for the staff, as well as profit, of course. And there was a contingency given of about 25%. Here's a look at how we've taken this project from the ground up throughout the year. Back in the fall was a lot of kind of figuring out what the city was looking for specifically. And over the course of the spring from January up until today was a lot of the final design, the iterations, and just making sure that what we had was what they were looking for. And then those red boxes that you can see there are milestones such as pinups or presentations.
For sustainability, pre-engineered metal buildings are effective and energy efficient. And the insulation that makes up the structure helps sustain heating and cooling temperatures inside the building, especially with the glass facade that lets that natural light enter the building. And steel is heavily reusable, meaning that material during construction is recyclable. For the environment, we have a minor impact on the surrounding environment since construction time for these types of buildings is low. And given that the location is on a golf course, green space incorporation won't be difficult.
For our final design, we decided to go with the pre-engineered metal building, but this time with a sloped roof. It's a rigid frame that is often tapered to save weight, as you can see on the right side on the image. It includes girts all around the building to support the columns and purlins on top for the roofing, which is used to support the roof deck. They are known to be affordable, low on maintenance, and more eco-friendly. We decided to use glass panel all around the building for the natural lighting that the client wanted. We used SAP 2000 to design the building and also analyze the seismic load to see how the building will react the currents to like an earthquake. Although it's not really our primary concern, but it's always good to consider just in case of any surprises. And on the bottom, you can see two images. The left side will be the deformed shape of the building, and on the right, you can see all the stress and force acting on towards it. We want to thank everyone for your time, and we're happy to answer any questions that you may have.
Great. Thank you, team member 3. Questions from our audience?
One question about the budget. The 25% contingency, how did you came up with that percentage? Was the thought process behind it?
So before meeting for the final time with our client, this was not considered. However, upon seeing the budget, they had proposed that we add a 25% contingency, as this was a number that they were expecting to see from the city.
Okay. So that was really suggested by your client.
Yes.
Thank you.
I have a question related to one part of your presentation, which was great. Thank you very much. You talked about considerations for weather variability. Was there any investigation into precipitation data over the course of time when you were factoring that in?
Are you talking about for the sustainability just in general?
Correct.
So I think when we went with the sloped roof, it kind of helped. We don't have any data specifically on the amount of rain in Maryland per se, but I think a curtain wall could be useful also to protect the building against water penetration. Obviously, it's a glass facade. So I think that's definitely something that the client can look into. Obviously, it'll be more expensive, but that could definitely help with the water penetration from any rain.
Thank you. Great presentation.
Hi, this is Dan Murphy. I had one other question. You mentioned that you were going to not have an elevator. Did you look into any other solutions for moving materials for during the actual opening and operation of the building between floors?
Not extensively currently. However, there was always kind of a consideration for that. We never took it any direction. However, there would likely be some kind of exterior lift to provide a little extra mobility to ADA compliancy.
What about materials? I'm thinking, from a HVAC electrician, if you bring in equipment or anything else up and down, even like cleaning materials or whatever you may have, that you might need to have some level of ability to move things from one floor to the other.
I believe, at least for as far as construction goes, there was a little bit of consideration in the budget for a lift to move between floors. However, I can take a look at that and get back to you if you would like.
That's fine. Thank you.
Great job, Team 3. Let's give them a round of applause. We'll move to Team 4. If you can go ahead and share your screen.
Good morning. I'm Sam Gavareski, and working alongside me is John Abruzzi and John Devlin. Our project is the Eccles to Martin Tunnel and Connection design. Our purpose for the project was to redesign the tunnel running between the Eccles and Martin buildings, as well as the tunnel connection for the Eccles building for the Federal Reserve. Both the tunnel and connection were constructed in 1970, and as a result are very outdated. They're currently not even in use and must be updated so that the employees at the Federal Reserve can easily access both of the buildings. Some design goals that we had for the project were to design the tunnel and tunnel connection for easy access and comfort. We wanted to make the tunnel feel like an above-ground hallway rather than an underground tunnel. This would ultimately make the employees feel more comfortable and enjoy their time walking between the buildings. Another design goal that we had was to match the aesthetics of the Eccles and Martin's building, to have a modern look but still have the historical feel. The final design goal we had was to design sustainably, and this will be discussed more in depth later on in the presentation. For some background, as previously mentioned, our client for the project is the United States Federal Reserve. The project is located on 20th Street Northwest and Constitution Avenue at the Eccles and Martin building in Washington, D.C. The original focus of the project was the underground tunnel located below C Street between the Eccles and Martin buildings. The tunnel is made up of 3 sections: a pedestrian tunnel, a utility shaft, and a service tunnel. However, after our site visit, we determined the best course of action would be to put our main focus on the structural efforts for the tunnel connection and the architectural efforts for the pedestrian tunnel and the tunnel connection. The connection will allow for movement between the main floor or concourse floor and the newly renovated ground floor or basement area. Both the tunnel and connection could be used by approximately 500 Federal Reserve employees per hour moving between the 2 buildings, so it is critical that the space is optimized and used efficiently. Shown in the pictures on the slide are the current conditions of the tunnel connection in the Eccles building. As you can see, there's currently a staircase against the left-hand wall and 2 old out-of-use escalators. It is also out of code as there are no ADA accommodations, so in our design, we include elevators that span all 3 floors. Furthermore, as you can see in the picture on the right, the ceiling curves down. In our design, we flattened it off to maximize overhead space and open up the connection. Shown in these pictures are the current conditions of the underground tunnel between the 2 buildings. During our site visit, we were only able to see about a quarter of the tunnel, so we assumed that this is what it looked like through the entirety. As you can see, the tunnel does not have any finishing. It has exposed HVAC and concrete on the walls. The ceiling and the floor are both made of concrete and there are exposed beams on the ceiling. From our design iterations, we decided to move forward with 2 designs for the tunnel connection. Both designs include a scissor staircase and 2 elevators, allowing for easy access and movement between the 3 floors. Again, for both designs, the elevators need to be put into the wall, so whatever is behind it will need to be relocated. We were sure that this would be acceptable by the Federal Reserve. To the left is our no platform design. It is comprised of the Eccles building main floor at the top, with a landing for the elevators on the back right, as the elevators can open on both sides. The tunnel floor, which is the intermediate floor, and a basement floor. To the right is our platform design, where the major change is that instead of a landing on the back side of the elevators, there's a platform connected to the stairs for the people to get off the elevators. The currently displayed floor plans are for the platform design. Pictured on the left is our floor plan for the Eccles building main floor. Coming from the tunnel, there are stairs leading down to the basement against the left wall. To the right of those stairs are stairs leading up to the main floor. Connected to the stairs coming up and the hallway is a platform that allows for people to exit the elevators on this floor. As previously mentioned, the ceiling that is currently in the connection area will be flattened off as suggested by the Federal Reserve to allow for more headspace. It was assumed that the electrical systems, plumbing, and HVAC located there could be moved. Pictured in the middle is our floor plan for the tunnel floor. Coming from the tunnel, there's a flight of stairs going down against the left wall. Next to that is the flight of stairs going up to the hallway. And to the right of the stairs going up is a column that supports the platform. And then against the right wall are the 2 elevators. Pictured on the right is our floor plan for the ground or basement floor. We were unable to see this on our site visit, so it was assumed that where the stairs, column, and elevators descend is acceptable. The overall purpose of this design was to allow access to all 3 floors and stay contained to the connection area. The floor plans that are being shown on the slide now are for the no platform design. On the left is our floor plan for the Eccles building main floor. The changes that were made to this design is that the stairs were pushed back towards the hallway by about 4 feet, and the platform to the right of the stairs going up to the main floor was removed. Instead, there's a landing on the other side of the elevators that leads around the elevators into the main hallway where the stairs also lead. The elevator has double-sided doors, so it'll be able to open on this side as well. Shown in the middle is our floor plan for the tunnel floor. The only major change to this design is there is more overhead space where the elevators are since there's no platform. Finally, shown on the right is the basement floor plan. The design for the basement floor is pretty much the same, but the column was moved since the stairs were also moved. We made this design because it opens up the connection area and maximizes the overhead space and makes it feel less cramped within the connection area.
I will be taking you through the renders for both designs. Throughout the designs, we use marmoleum flooring and white low VOC paint for the walls and ceiling. We also use glass railings made from recycled material with stainless steel railing or handrails and energy efficient 5-foot long LED light fixtures. We will discuss the sustainability and key features of these materials at a later time. I will show you the same image for both designs back to back with a no platform design being shown first. The first image shows the view upon leaving the tunnel and entering the connection on the tunnel floor. And this is the same view of the platform design, showing the view of the connection upon leaving the tunnel. The next image shows the view of the connection from the tunnel. Inside the tunnel to the left is a digital wall screen that will display images of the client's choosing and is currently showing the exterior of the Eccles building. The screen is from Imagine Screens. This again is the view from the tunnel for the platform design, showing the same digital wall screen. The next image is a viewpoint from the bottom of the stairs up of the basement floor up toward the rest of the connection and the tunnel for the no platform design. And this is the same view from the bottom of the stairs to the basement floor for the platform design. Next is an image looking down toward the connection from the Eccles building main floor. This is of course the no platform design. And finally is an image looking down toward the connection and tunnel from the Eccles building main floor for the platform design. Shown here are the layout sheets and dimensions for the elevators and shaft. We selected a machine roomless elevator or MRL elevator from Schindler Elevator Corporation. The plans on the left are for the double-sided elevator for the no platform design, and the right for the single-door elevators for the design with the platform. Each elevator has a capacity of 2,100 pounds and travels at a speed of 150 feet per minute. They only operate at 50 decibels of noise, which is the equivalent to a quiet conversation at home. The elevator will be supported by a surrounding shear wall system with I-beams at the top going across into steel plates. The loads that are to be applied to these beams were given us by the Schindler Elevator Corporation and will be discussed later on.
The following slides are SAP 2000 models for the tunnel connection. SAP 2000 offers the use of templates for different structures, but we opted for going with the custom AutoCAD models using a finite element method. The custom models gave us the maximum amount of creative freedom and control over our designs. To create the custom models in AutoCAD, the slabs and stairs shown by the red squares on your screen had to be drawn as 3D faces in their own layer of the drawing. The frames shown by the blue lines were then modeled as line elements in their own layer on the same drawing. The drawings were then able to be imported into SAP. SAP would read the 3D faces as a customizable mesh while reading the frames as beams, columns, and lateral bracing. Lateral bracing was used to prevent collapse of the structure once it experiences horizontal loads. From there, we began applying the dead and live loads to the structure. All standard dead and live loads were taken from ASC 716 An extra 15 PSF live load was applied to the structure to account for any utilities. There's also 60 PSF contingency live load applied to the structure. This load will account for any future desired changes to utilities by the client. After applying the loads, analysis was then run on the structures. We have chosen to use steel W sections for the beams and columns and HSS sections for the lateral bracing. Using SAP's steel design function, we were then able to determine whether the sections we chose were suitable. We started with W4 beams and columns and small HSS sections for the lateral bracing and ran individual analysis on each beam until the structure was safe. We then collected a range of safe steel sections for beams, columns, and lateral bracing. We created and applied an auto-select section for each different framing type that was comprised of all the safe sections for the respective frames. When structural steel analysis was run again, SAP would optimize the design by applying the most efficient section to each individual frame. After reviewing SAP's new analysis with our own iterations, the specific frame sections were finalized for each design. The first connection design is the platform design, and this slide shows a 3D view from SAP. This is a wire mesh view of the platform design with the joint restraints highlighted in orange and green. The orange represents fixed restraints that can also be used for floor continuation. Since the main floor of the Eccles building continues far after our design, fixed restraints were used to show this continuation. The green represents springs. These springs were applied to the basement floor as the foundation is assumed to be resting on a structural soil. The springs also serve as a restraint for the front part of the elevator shaft. This slide shows a deformed view of the platform design connection. After running the steel analysis, we had to check for the deformation values of the structures. We checked for 4 main deformations in the structure: the new platform on the main floor labeled A, the tunnel level floor labeled B, the basement floor labeled C, and the elevator landing on the tunnel floor labeled D. The deflection values were 0.18 inches for A, 0.23 inches for B, 0.06 inches for C, and 0.18 inches for D. The second connection design is the no platform design. Because this design requires the elevators to open on both sides, the back wall of the elevator shafts cannot be braced with regular lateral bracing. Instead, we use small chevron bracing sections to support the shaft. This slide shows a 3D view from SAP. Again, this is a wire mesh view of the no platform design. Just like with the platform design, the joint restraints are highlighted in orange and in green. The floor on the left side of the black line is surrounded by walls, while the floor on the right side of the black line is open to a main area, making the joints fixed connections. Springs are used and located in the same areas as the platform design. And this slide shows a deformed view of the no platform design. Again, we checked for the four main deformations in the structure: the new corridor labeled A, the tunnel level floor labeled B, the basement floor labeled C, and the elevator landing on the tunnel floor labeled D. The deflection values were negligible for A, 0.29 inches for B, 0.06 again for C, and 0.21 inches for D. And then this is just a breakdown of the finalized steel sections we used for each design.
For a design to be sustainable, we wanted to reduce consumption of non-renewable resources, minimize waste, and create healthy, productive environments. Furthermore, we wanted to increase the lifespan of our design so it does not need to be updated for a while. To make it sustainable, we used environmentally preferable products like marmoleum for the flooring, recycled materials for the glass railing, and low VOC paints for the ceilings and walls. Marmoleum is made from raw materials taken from living plants that absorb CO2, thus making it CO2 neutral. It is also a very durable material that can last over 30 years. The glass railing was designed with recycled glass, as glass can be recycled without loss in quality or purity and can be substituted for most raw materials. The paints used in the design for the ceiling and walls are low VOC. Low VOC paints give off relatively no odor, dry quickly, provide good coverage, and offer a durable finish. They enhance indoor environmental quality by emitting little to no volatile organic compounds compared to standard paints. Our design also strives to reduce non-renewable energy consumption. The machine roomless elevators in our design use 70 to 80% less energy than standard hydraulic elevators and do not use oil, so are not a fire hazard like most. The LED lights are energy efficient and durable, which will cut back on maintenance costs.
This is just a preliminary cost breakdown for both the no platform and platform designs. The total cost at the bottom show rough estimates of what the just the materials for each project would cost. with the no platform material cost being $894,097, and the platform material cost being $857,127. And with that, we thank everyone for listening and conclude our presentation. We'll be happy to answer any questions you may have for us.
Great, thanks team. Questions from our audience?
I have one question. So from a cost standpoint, what accommodations or considerations did you make as it relates to tying to the existing building or working inside the existing building?
Devin, can you go back to this slide? Yeah, so we part of I guess is we can get a lot of information about the existing building. Really, the only information we got was what we saw on our site tour. We were there, and one of the things the client told us was to kind of design the connection as if it was like not a standalone structure, but not to worry about so much the other features of the building. So just design it as its own separate entity, and then connect it how we need it to the tunnel and to the rest of the building. So we mainly focused on just the area we worked in.
Okay, so just for my understanding is that this is assumed that, but it is inside the footprint of the Eccles building, right? Okay.
Yes.
All right, thank you. It's fairly complex, yeah. Good job.
Any other questions?
Yes, hi, this is Dr. Laura Micheli. This is very good presentation. Congratulations, guys. This is actually a very peculiar project. So I was curious to know what was the most challenging part of the project?
I think the most challenging part, besides learning how to use all the programs like SAP and AutoCAD and Revit, was dealing with the lack of information. And the original focus of our project was supposed to be on the tunnel and redesigning that. We thought it was going to be a structural redesign of the tunnel, but then later in the project we found out that it was better to just shift our focus to the connection. So just using what we learned from SAP and applying that to the connection design was challenging, but we enjoyed it. We learned a lot from this project alone.
Great, thanks team 4. Let's give them a big round of applause and move to team 5. Team 5, can you share your screen?
Yep, sure, just a moment. So can you see my screen?
Yes, we can.
Okay.
So hello everybody. So today we are presenting our project, which is redesigning John McCormick Road with my teammates, Abdullah Al-Mutairi and Fahad Al-Anjbi, and me, myself, Mohammed Al-Shimiri. So basically our mission is to ensure and maintain the engineering codes provided by the DC government. Discussing the needs and challenges is going to be one of the main priorities with our client, which is Catholic University. Discussing the needs and challenges is going to be one of the main, the future project manager will focus on different areas of the project and test different ideas with the client. Safety is our main concern, and having easy vehicle access for everyone. Can you go to the next page? So for our project location, it's on John McCormick Road and Michigan Avenue, focusing on the pedestrian crosswalk between the metro station and between the campus and the metro station, and also focusing on the intersection between John McCormick Road as well. On the first picture as identified, the grass curb is an impediment, which means vehicle traveling at John McCormick Road need to take a long path to access Michigan Avenue. On the second picture as shown, the pedestrian crossing do not force the motorists to stop before the crosswalk, which make it unsafe for the pedestrian to cross from the metro station to the campus.
So in this project, we use two softwares. The first software is Autocad to provide a design for the project, and contains dimensions, details, and solutions. And we also used Amphitheater traffic simulation system to test out our design and to see if it's efficient and works accordingly, and also to provide dynamic traffic simulation. So as you can see, here's our AutoCAD drawing. Where I'm pointing is John McCormick Road width is 30 feet, and also 1 foot gutters for each side. And also Michigan Avenue width is 40 feet width, and also 1 foot gutters for each side, which is the total is 42 feet width. And the stop sign are to be placed on the pedestrian crosswalk, as I am pointing over there. Also, on-street parking is to be added in the room between the pedestrian crosswalk and the parking lot entrance. In addition, expanding a new lane will result in 20 feet width, and that will be divided in 10 feet width for each lane after the parking lot entrance, which allow vehicles to turn into opposite directions toward Michigan Avenue. It also shows intersections, road directions going to and coming from John McCormick Road. There's existing concrete and metal fence over the bridge, which is above the metro rails, which contains the sidewalk that's bike accessible to travel on towards John McCormick Road and Michigan Avenue. So here is the stop sign on the pedestrian crossing. The crosswalk shown in the picture is mainly used by students to access campus from the metro station, while the speed limit of John McCormick Road is 15 miles per hour as it's a school zone. Motorists often travel at higher speed, although pedestrian sign already exists. Preliminary research was conducted through AIMS and traffic simulation software to reduce the chance of pedestrian occurrence. The options found are either to place a stop sign or traffic signal. Due to cost efficiency and practical effectiveness, the installation of a stop sign was the preferred option. This option is easy to install and will force motorists to reduce their speed at the crosswalk and stop for at least 3 seconds. According to the law, the stop sign should be placed at least 6 feet from the pedestrian crossing. However, reckless drivers often overstep the crosswalk lines and stand in the way of pedestrians. Therefore, to ensure pedestrian safety, the stop sign will be placed within 8 feet. Also, AIMSN has proved that the stop sign is efficient and decreases the risk of pedestrian accidents. And for clarification, there are stop signs as shown in the picture, and that's only through AIMSN traffic simulation software. But in the actual design will be only 2 stop signs, and John McCormick Road will be placed one, and the northbound will be placed another one. So here is the signalized intersection. As we are resurfacing the road by expanding a new lane toward Michigan Avenue, a traffic signal is to be installed as shown in the picture. The new lane will use to turn into opposite directions. 2 other traffic signals are to be installed in Michigan Avenue, where I am pointing. In addition, a left turn signal must be added to allow vehicles to turn into John McCormick Road, which is this signal. The intersection's traffic cycle will be 100 seconds. Michigan Avenue's traffic signal will turn for green for 70 seconds, including the 5 seconds duration for the left turn, while John McCormick Road will turn for 20 seconds. Michigan Avenue is prioritized as is the main thoroughfare. Furthermore, the yellow traffic timing is 10 seconds for the entire signalized intersection. So here is our design development analysis. As we're placing the stop sign on the pedestrian crosswalk, it will be 30 by 30 inches and 7 feet height from the ground to the bottom of the sign. It will be placed within 2 feet from the curved roadway. And also the standard width in the District of Columbia range from between 10 to 12 feet. As John McCormick Road is a minor street, the lane width will be 10 feet for both lanes. And the standard curb thickness in Washington, D.C., which is applied in our design, is 7 inches. In addition, the gutters should be 1 foot between the roadway, and it's also applied in our provided design.
Design constraints. With design signalized intersection comes a number of constraints. These constraints are due to the location, time, and budget. These constraints help us identify more suitable and economical solutions. First, bike accessible. During the design of intersections, bikes cannot be ignored. Number of traffic comprises bikes. Therefore, the intersection should be bike accessible. Then, appearance. In this project, considerations, a quality road appearance form a beautiful combination with environment. A driver can wait in a place having a good appearance. The journey becomes joyful if the roads are beautiful. Then on-street parking is one of the major concerns in this project. As the location is a busy place, SKC has to accommodate a few parking spots during school business hours. Therefore, the design must consider the location and its schedule. Then deadline constraints. Final design of the project delivered on May 4th to the client. For the next slide, you will see sustainability. First, reusing concrete. Using recycled concrete can reduce construction waste and costs. It reduces environmental pollution by replacing gravel and staying out of landfills. It also conserves natural resources and is less costly. Recycled concrete will be used in paving the expanded lane, which helps saving disposal and transportation costs. It's helpful for the long run of sustainable development. Then, reclaimed asphalt pavement is the expression given to remove pavement materials, including asphalt and aggregates. In this development, asphalt is used instead of cement or other binders. Asphalt is environment friendly and less costly. In addition, it has a high load bearing capacity and durability that makes it sustainable. Then, eco-friendly light. In this project, the traffic signal bulbs used are LEDs. Although they cost more than CFLs and incandescent bulbs, they consume less power per unit and last 3 to 25 times longer. It typically uses about 25 to 80% less energy than the other example mentioned above. One LED bulb decreases greenhouse emissions by almost half a ton bulbs because they don't release a high amounts of carbon dioxide. For the next slide, you will see the estimate cost, the cost estimate. First, purchase and install intersection traffic light. We have 3 traffic lights. Each traffic light costs $250,000 and the installation costs $750,000. So the total will be 1.5 million. Then the purchase 2 stop signs and its installation. Each stop sign costs $100 and the installation cost $1,000. So the total will be $1,200. For traffic lights, electrical bills and routine maintenance yearly will cost $40,000. For the expanding a new lane will cost $1 million, $375,000. Our group have visited the site and we found road damages such as cracks on the intersection. As we are doing lane expansion, at the same time the constructions will be working repairing the existing road damages, which range between $250,000 to $6,000 based on how the damages are. So the total cost will be $2,919,000.
So here is our dynamic traffic simulation through AIM-Syn traffic simulation software. So as you can see, there is here's the intersection of between John McCormick Road and Michigan Avenue, and how is the traffic regulation works. As you can see now, John McCormick Road can access Michigan Avenue safety and accessibly. So now is our dynamic traffic simulation for the pedestrian crosswalk after placing the stop sign. So here's people can cross the crosswalk safely, and the vehicle has to stop at least 3 seconds, and also 8 feet distance from the pedestrian crosswalk as shown on the video. Thank you so much for listening, and we are happy to answer any questions.
Great, thank you, team. We'll have questions from our audience.
One question. Google's presentation. So did you give any consideration of the duration of the actual construction work schedule?
Actually, we had the schedule from like the design, which started like last semester, until delivering the design to the client. But we didn't like exactly consider how long is it going to take to the construction to work on site.
Mm-hmm.
Yep.
All right. Thank you.
Great. Any other questions?
I have a quick question. So the price of the traffic lights looked a little. I mean, I have no idea what the price is, but it looked too high for me. Is that the price that you came up with correct?
Yeah, actually, we looked in different resources through different like transportation companies. It's cost, and it ranges from this pricing, which is $250,000 for each signal, because it has like electricity and installation, like, and linking that to other signals, and that's from different resources, and that's what we came up to that price. And it might be less if it's we found like another construction company that can do it less than this price, but that's the price that we came up in different resources, to be honest.
Okay, interesting. I think someone should go to the business of making traffic lights.
Yeah, that's true.
Okay, thank you.
Thank you.
Well, great job. Let's give them a round of applause, and we'll move to our next group, Team 6.
Do you guys see everything?
Yep, you're good to go.
Excellent. All right. Well, we are Team 6, Amanda Labasi, Molly O'Connor, and myself, Christopher Dzinski, and we will be presenting our camping and park infrastructure proposal for Cayman Island. So, Cayman and Heritage Islands are located in the middle of the Anacostia River, directly east of the RFK Memorial Stadium. There's only 2 pedestrian access points to the Cayman Island Park currently, one bridge that crosses from the Heritage and Cayman Islands from the fields at RFK, and a gap in the park's fencing along Benning Road Northeast, which is the furthest north the park extends on the island currently. Our primary client was Councilmember Allen, with a contact through his aide for Chris Laskowski, but we also wanted to consider the interests of a group called Living Classrooms, who currently hosts many events on the island. They're a nonprofit organization in the DC and Baltimore area that focuses on teaching students in local natural environments. During our team's site visits, we noted that while the park sees a lot of foot traffic, the conditions are subpar. There is little to no park infrastructure. A makeshift storage dump currently sits along the main walking path, and the soil conditions on the island are poor in most areas due to being easily floodable. However, DC wishes to keep the park mostly wild, so any park additions must keep a minimal footprint and effect on nature. A major challenge for the park is Cayman Island's susceptibility to being flooded. Significant portions of the island flood frequently and are inundated with rainwater very easily. The river level has risen up to 5 feet at some point each year during heavier storms, on average, and the 100-year flood mark covers most of the southern portion of the island as well as all of Heritage Island. Both the 100-year and 500-year flood levels are likely to happen more frequently in the near future, and as such, our placement of the restroom and amphitheater improvements, which we will go into, needed to account for this. So, our master plan components currently includes roughly a 110 tent pads and sites to be set up with needed soil remediation, cleaning, and proper access to potable water. We also included a prefabricated bathroom option as there's no restroom facilities currently on the island. This option was designed heavily off an option from the company called Green Flush Restrooms, which we'll go into in a bit. We designed an outdoor amphitheater option for hosting events and also as a primary classroom for living classrooms. And we made some small additions to the park, such as benches, picnic tables, signage, and other elements. Here's a look at the current zones of our master plan. We have proposed classrooms at 3 different points marked in red, with campsites separated out along the park's main path in different small clearings. The park's new restroom facility will be located along the Heritage Island entrance path with new outdoor amphitheater on the southern side of the path and clearing. This is a closer look at the entrance from the Heritage Island and the clearing where the new restroom facility and amphitheater will be located. I will go into both of these options later on in the slides.
For the campsites, we have proposed 110 sites of different sizes to be placed throughout the island for visitors to camp overnight. Each of these pads will be composed of a 4-inch sand and gravel mixed layer that will be laid on top of infill soil gathered from the construction of the nearby amphitheater in order to reuse all the materials we are removing from the site. Each of these campsites will also have access to the main path, potable water, and the restrooms. In order to provide proper drainage from head to toe of each of the camping pads, as well as maximum comfort for the campers pitching their tents, the approximate slope of each pad is about 0.1%. All of the campsites have been designed to follow the existing contours of the island in order to minimize the amount of impact needed to set up the sites, as well as allowing current drainage paths to be maintained on the island to prevent further flooding issues.
Looking at our bathroom option, we've currently designed it to include 2 stalls for men and 2 stalls for women, as well as 2 family bathroom spaces, which are ADA compliant and can be entered from different doors in the system. This system also offers the potential to incorporate rainwater collection, as well as the reuse of sink water to flush the toilets. And this was one of the primary reasons we chose Green Flush Restrooms, because of their ability to incorporate sustainable options. The design from Green Flush also includes toilet systems which are nearly 70% more efficient than conventional toilets. And because the system is prefabricated, it can be installed in the span of days and is much more affordable than a custom system. This is a rendering of our design option based off of Green Flush's system, with our amphitheater in the background in that park clearing that I mentioned before. Looking at our amphitheater option, it is situated into a natural curve in the hill on the southern side of the clearing in Heritage. Only some excavation will be needed to remove the soil, which will help with the remediation of campsites, in that the minimal soil we're moving is very good quality compared to the soil which is poor throughout the rest of the island, and as such can be used to regrade those tent pads. As I said before, this space can host living classrooms and will be a good space for the Bluegrass Festival event, which happens once a year on Cayman Island. The current design showcases 3 different possible seating options as well, which could either be made up of benches or rocks. Here's a look at our section design for this system. The most important data to note here is the 6 terraces which make up the seating arrangement, each of which is a foot and 10 inches increase in height from the next level. Here's another rendering view of the seating arrangement for that amphitheater with the possible different options included. We also had to go through multiple steps of structural analysis for 2 primary structures in this project, mainly the roof cover system for the entrance between the bathrooms and the roof cover for the stage of the outdoor amphitheater. Using SAP 2000, we were able to analyze the timber structures and to determine the sizes necessary to make a sufficient system. For the bathroom entrance in particular, we ended up using 8-inch by 8-inch timber columns to support a metal panel roof. And then for the amphitheater system, we used 18-inch by 18-inch timber columns to support a timber frame with shingles. That structure in particular proved to be much more difficult and had to go through 3 iterations before we found something acceptable. The rest of the framing is mostly 2x4 wood beams, and as such, these results are the final. For our footing systems, for the retaining wall, for the amphitheater terraces, we had to go through 3 different versions. We had to do checks for sliding, overturning, and soil bearing failure, all of which were completed by hand. And as such, this is our final design detail section.
So Cayman Island can be broken down into 47 drainage areas, which we have analyzed for flooding inflicted by our proposed designs. Our biggest impervious impact will be in the clearing area, where we have proposed about a 0.06 acre increase to the impervious area to the roughly 3.3 acre clearing area. And therefore, this is the area that we chose to focus on for this analysis. While our additions to the site are minimum to offset the effects, we will be installing an approximately 100 square foot by 2.5 foot deep bioretention bed that will assist in the infiltration of water back into the ground in the area after a storm event. The cross-section of this bioretention design is specified on the slide, beginning with a mulch top layer, followed by multiple layers of soils and gravels designed to filter and infiltrate the rainwater back into the earth without flooding. The table above provides us with the pre, post, and post-stormwater design high groundwater levels, or HEAD, which shows the positive impact this bioretention bed will have on our site. In the table, you can see that from pre to post design, the water levels and therefore the potential for flooding increases. In the last column, however, you can see that the addition to our stormwater design with the addition to our stormwater design, those groundwater levels match the pre-development conditions, and in some storms will even improve the groundwater levels that currently exist. The graphs provided are taken from our PC swim model and depict the slight increase in the total head after our impervious additions were accounted for. While minor, it is important to us to mitigate all possible flooding situations as we sit in a flood zone.
So because our restrooms are located at a low point in comparison to Benning Road, the cost to connect to the DC sewer line would be too high due to the need for boosters in order for the sewage to be able to meet the main line. It was chosen to install a 5,000 gallon septic tank that will need to be emptied annually. These sizings are based off our toilets flushing 1.1 gallons per flush with about 200 users per day. As a measure of safety in the calculations, there is no differentiation between the use of a urinal and a toilet. All flushes are considered to be a toilet, which uses a greater amount of water per flush. The sludge and scum calculations account for the solid waste that will be entering the septic tank and settling at the bottom of the tank. We chose a 2-chamber septic tank because it provides better settlement of the sludge and scum and separation of solid waste from the water compared to a single chamber septic tank. With this information, we had the opportunity to go in 2 different directions with the design: a custom septic tank or a prefabricated septic tank. Due to the cost constraints of the project, we decided it was best to choose the prefabricated septic tank. It is also important to note that during large events on the island, we propose that there needs to be porta potties placed throughout the island as a measure of safety to not overload the septic tank. So the cost estimate shown is based on current industry trends, including the lumber shortage that we're seeing in the construction industry. The cost per site includes the installation, labor, and materials. The modular bathroom is also a fixed cost provided by the manufacturer that includes the physical modular bathroom as well as the manpower needed to install it and all necessary equipment. The amphitheater is a lump sum cost for the materials, equipment, and labor based off of example projects throughout the US of similar size amphitheaters. The trash removal is a large variant cost that will fluctuate throughout the project. And our landscape improvements and bioretention will include a lot of flower beds and visual aspects on the island to ensure the bioretention adds to the natural look of the landscape of the island. The classroom section has an allocation of money that will allow for the development and improvement of the living classrooms. And then for the impact on the environment, our biggest goal in this project was to make sure that people were able to come and enjoy nature within DC because it's such a large city that has a lot of concrete and all of that. So our main goal was to minimize the impact of our excavation and leave the vegetation in the area for construction and all of our additions. So our 110 campsites are proposed to be in already existing clearings, meaning that we will not be removing any trees from the island unless completely necessary. The environmental impact of our tents is also extremely decreased by reusing the excavated soil from the amphitheater. So overall, we wanted to leave a very small impact on the island while making a big impact on the city. And with that, we thank you for listening and we'd love to answer questions.
Thanks, Team 6. Questions from our audience members?
I have a question. Very good job. As far as the access to the site, both for construction and later for cleaning the septic tank, is there vehicular access to the island currently?
Yeah, so there is a vehicle access point on Benning Road. So when you come onto the island, it's like a gated area on the main road and you can drive a vehicle down it up to a certain point. There is
So there's no additional cost to make access there.
no, so the access is already there. So we wouldn't have any further impact on the island or cost.
Great, thanks.
Yeah, I have a quick question. Are there like annual maintenance for the tents in the amphitheater that you were thinking of? And if so, did you have like a projected cost for this?
So we did not account for any of that. Obviously, there would be maintenance of it. And I think that'd be something that you would see once the installation of the pads is done based off of like storms and all of that. You'll see how the soil reacts. But currently in that budget, there is not maintenance acquired.
Thank you. Very nice presentation.
Do we have any more questions? All right, so let's move to our next team and give a round of applause to Team 6. Now we're going to be moving on to Team 7.
Just want to point out something very quickly. So I had scheduled this event for 2 hours. Now it seems like we may go beyond that, which is fine. So we have another meeting between the advisory board members and the graduating seniors, which is scheduled on 10:15. If we have to, we will just maybe delay that a little bit. So we can actually, if you don't mind, we can actually go beyond the 2 hours time.
All right, thanks, Arash. So Team 7, when you're ready, you have the floor.
Hello, everyone. Welcome to our presentation on Catholic University's West Campus Master Plan, a modern take on the campus green. So introducing our team, we have Chris Johnson, who is in charge of sustainable design as well as structural analysis. Myself, Nick Persino, in charge of transportation analysis, and then Jordan Bryant in charge of water management.
Nick, sorry to interrupt you. Could you try refreshing your page, or can someone else share their slides? It's highly pixelated right now.
Do you see this currently?
Yeah, is it pixelated on everyone else's screen, or is it just mine?
It's yeah, it is. Actually now it's a little better.
Oh, I can see fine, so.
Okay. Okay, now it's a lot better.
Okay.
All right, great.
Try
Thanks,
that
Nick.
again. So welcome everyone to our presentation on Catholic University's West Campus Master Plan, a modern take on the campus green. So just introducing our team, we have Chris Johnson in charge of sustainable design and structural analysis, myself, transportation analysis, and Jordan Bryant was in charge of water management.
Here is a general overview of the project. We have designed a 30-year master plan for CUA's Western Campus across Harewood Road. For this phase of the project, we focused on the underground parking lot to design it to be future-proof, meaning that it can be modified as the needs of campus change in the 30-year span. And we also looked at further analysis of the site design. Here is the final iteration of CUA's West Campus. This is built to be the successor to CUA's current 15-year master plan, and we chose to build on this spot so as not to disturb the forested area. Entering from Harewood Road and following the University Drive, you're able to park at the underground parking garage. There is a central quad formed by the traffic circle, Caldwell Hall, and two main buildings. These main buildings would be administrative or, if needs be, classrooms. At the far north are individualized houses for graduate students or faculty. For major street crossings, there are raised crosswalks to prevent speeding, and we also plan for this to be a fairly walkable site and have planned space for bikes. In the discolored green areas are planned bioretention beds to prevent flooding, most notable along Harewood Road. You'll hear more on that from Ms. Jordan.
So in the fall semester, we conducted a student survey of a random group of students. About 20 responded. And based on this, we used it in our design. So we asked three simple questions. In this new development of campus, would you prefer large structures or more of a small town, quote unquote, Main Street feel? Of that, you can see that a majority of them would like a Main Street feel. In the second question, would you be interested in internship or work experience opportunities offered in this new complex? A large number again said yes or maybe. So we did that in our further design of the parking garage. You'll learn more about our modular design and how we incorporated this question into that. And the third, a mix of both for entertainment complex. So it's going to be academic. So we had our academic buildings, and we were going back and forth on the movie theater bowling alley, but we focused more on the quad and making that a more inviting space. So that was more of a recreation part of the entertainment complex.
Thanks to our survey, we were inspired to create Main Street CUA. It may remind you of Main Street USA a little bit. Main Street CUA is meant to further the feeling of home on campus by incorporating a small town feel. The building is broken down into substructures with different heights to give the impression of a row of townhomes or small shops. Along the bottom is a silhouette of the building skyline, just to give you an idea of how it would look as a whole. The interior includes classrooms and sitting or study rooms, as well as offices and meeting rooms as well. The rooms fit into the substructures and each has its own separate exits and entrances, but they're interconnected through the building as a whole. Fire doors separate each substructure. Each of the buildings also connects to the garage via an elevator and a fire stair. The image to the right is a render of North Hall by Harewood Road.
We designed an underground parking garage for this master plan. At the professor's behest, we have gone into detail about the various aspects of its design. Here we are looking at the structural capabilities. Using a program called SkySieve, we were able to design the details shown below, as well as analyze the grid for any potential problem areas. We acquired a variety of diagrams that show shear moment diagrams and bending moment that allows us to identify problem areas. Notable are the dark blue and dark red, if you want to click it, Nick. And dark red areas. These could be areas of concern when designing and may need appropriate consideration in the details shown below. And we see some of the concrete design at work. Each of these are designed for underground use and can for the most part accommodate the structure.
For transportation analysis, we looked at how to safely move vehicles and pedestrians across our site. University Drive along the bottom is the main road in which vehicles will travel between North Capitol Street and Harewood Road. University Drive is the main access road to the parking garage as well. For large transport, such as buses, they will travel along a day road, which for the southern portion is one way in the direction of south to north. There are intermittent raised crosswalks seen here in brown that provide safe access across the streets, let's say the nature walk. The combination of a traffic circle and the raised crosswalks allow for slow movement through the site, as Chris mentioned before, to prevent speeding. On the bottom right is a screenshot of the analysis we completed on the parking garage, testing its ability to handle cars. Here you see a GIF that we created using our early iteration of the site. So on the bottom, you'll see a car going up University Drive through the garage and back out. And then you'll see this large vehicle. It's a bus. We did this to test our roads to make sure we can fit a bus down the road and make all the curves. So later on the bottom left, you can see here, we curved a day road so that it is easier for buses to come down and stop, so they don't have to make all these turns and pedestrian and causing possible issues. So we did this so that buses can move straight through the site as well.
For water management, we use storm water management modeling, or SWIM, and green infrastructure flexible modeling, or GIFMod, to analyze our water management. SWIM was used to look at runoff across the entire site to prevent flooding of the roads. Across the bottom of the slide, you can see a section of our site from North Capitol Street to Harewood along the second path shown in the SWIM model to the right. There's over 27 feet of elevation change. In order to control the flow of runoff, we are excavating the slope ditch along Harewood Road. This was in the original plans for campus, and we found it was the most effective method in preventing the road from flooding. On the green above the garage, there are drains along the sidewalks to divert water around the underground structure to prevent pooling over top of it. GIFMod was used to focus on the parking garage analysis. The model to the right shows two drain conditions. On the left, the garage consolidates all the water that enters in a central drain, and on the right, the trench drain prevents stormwater from entering the garage at all. During a 30-minute storm, the water at the base of the ramp is reduced by more than 2 inches by implementing these, so obviously we'll be using them at both entrances. There are floor drains that are strategically placed throughout the garage to deal with the water that does enter. And in addition, models were created to simulate the removal of oil from the water before allowing it to infiltrate back into the ground.
And we designed this parking garage on a 29 by 20 grid. This allows for 9 by 18 foot parking spaces to fit easily in the spaces between columns. Due to the uncertainty of car usage, we also designed the garage to be modular with 4 main sections. And the back half can be built separately and has room to expand should CUA need the space. Alternatively, should car usage go down, the entire garage can be converted into something useful. For that, we have 3 ideas.
For our first iteration, we have an archival lab for the university. This lab will contain state-of-the-art technology to launch Catholic University into the future and to better preserve our great history. On the right third, there is the existing fire stair and the elevator that still allows access for the existing part of the garage. In the middle third, you have a computer lab space for researchers and archivists. And then the last third, all the way on the left, you have a storage space that is climate controlled for the preservation of Catholic's history.
Our second iteration, inspired by Dr. Davison, we looked into creating a hydraulics lab. Repurposing the modules of the parking garage provides the perfect opportunity due to the space required for the long flumes. We based our plans for this lab on the standards set by the U.S. Department of Transportation in their own testing labs, including a 70-foot tilted flume, as well as a force balance flume and the respective pumps and mechanics for each. Modular wall sections separate the computers from the flumes, though the computers still communicate with the pumps and sensors through the testing station in the back right corner. The physical models in the lab allow tests to be conducted under controlled conditions that help in the understanding of underlying physics. This means it can be used in a beginner capacity, such as demonstrations, and in advanced scenarios, such as testing theories and projects done by professors and graduate students.
In iteration 3, we looked at doing a hydroponics lab, also known as an underground farm. This lab would allow unique education opportunities and experiments with agriculture, while also providing chemical-free fresh produce. If this farm were to span the whole underground structure, it would be able to provide considerable food production for campus and the surrounding communities year-round with a bit of cheap student labor. And water usage can be offset by a rainwater harvesting system and would also score a few LEED credits for the campus. We proposed the creation of a nature walk through the undeveloped portion of West Campus. This could be jointly used by the residents of Old Soldiers, which are planning a complete redevelopment of their site right across North Capitol. And it would create a safe and active space for both students and residents. Further planning may see this turn into a prayer walk, or the space can be paired with additional rainwater analysis to allow the design for rainwater rehabilitation beds that would sort of force the rainwater back into the watershed. And that would also provide native habitat cultivation. And for habitat cultivation specifically, there are many interested parties that can help, notably Casey Trees and the Anacostia Watershed Society.
So we weren't really given a budget for this project, so we focused on our design and then created an estimate based on that. So we used current numbers for pricing of construction and materials in DC today, and use that to create a unit price per square foot of each aspect of our site. The module pricing varies based on use, but for our total cost, what we have planned is about $14 million, and that's for the entire master plan over the next 30 years, which we feel is pretty reasonable. Thank you so much. Can we answer any questions?
Thanks, team. Questions from our audience members?
Yeah, I have a quick question. Oh, I think Daniel, are you on mute?
Daniel, you are muted. Yeah.
I apologize. Great presentation. I hope I'm unmuted now. I had a question related to the project budget that you developed. What was the basis for using $4 per square foot for the landscape design?
So the way we came up with that, I'll pull it back up. So for landscaping, $4 per square foot, we tried to estimate dirt, plants. There was no, I wouldn't say that, I mean, you wouldn't really structure a budget on landscaping per square foot, but it was an easy way of trying to comprehend on our part what the general cost might be, but there was no specific way of going about it.
As well as showing you giving you a breakdown of the budget, because for example, the square feet that we planted, like for the rain gardens, had a significantly higher price point, while where they were just mowing the lawn was significantly lower, so it became the average.
Thank you very much.
Do we have any other questions?
I just have a quick question. I'm curious about like damage control for state-of-the-art equipment in an underground facility like this, and how confident you are in your stormwater management calculation.
So in addition to our stormwater calculations, we have very secure water membranes in place and drainage around the perimeter of the garage on the lower levels to avoid this. For some of the transformations, there obviously additional equipment needs to be put on the inside, such as the archives and like very intense climate control for situations such as that. So it really does depend on the planned use of the space, but the garage itself should be entirely watertight once it is converted. We're assuming obviously when it's used as a garage, water will get in, but that will not be coming in through the walls.
Thank you. Excellent presentation.
Great, thank you so much. Let's give them a big round of applause. And we have our last presentation, team number 8.
So, before team number 8 starts, I just want to point out to something. So it seems like we may go beyond 11:15 when our next meeting is scheduled. I would like to propose that we basically delay the next meeting between the advisory board and the graduating seniors to 10:30. And then the meeting after that, we're going to also delay it by 15 minutes. So we're going to finish by noon. That's all I have, if people don't mind. Thank you.
All right, great. So let's start with team 8.
Yes. Hello and welcome to everyone joining us today. Hadi and myself will be presenting our senior design Silt Fencing 2.0. Sorry, guys. Our design team is composed of 2 civil engineering students, Hadi Tanyas and myself, Sean Bartlett. Our design team was based on the James Dyson Award. The Dyson Award is directed towards young engineers who want to think outside the box and design a tangible product that will make a difference in society today. The award is judged on the inspiration, the development of design, and how the design is unique and how it benefits the future generation. Silt fencing is an inexpensive temporary barrier which is comprised of 4 basic materials: wire, geotextile fabric, wooden stakes, and metal staples. The true purpose of silt fencing is keeping in the soil sediment and debris on the construction site rather than letting it be washed off into our bodies of waters, such as streams, rivers, lakes, and ponds. The temporary fencing plays a huge role in preventing the degradation of aquatic habitats and siltation of harbor channels. The technical installation of silt fencing is comprised of 5 basic steps. These 5 steps are laying out the silt fencing and pulling it tight, trenching in order to bury the silt fencing partially into the ground, driving the stakes into the ground with a sledgehammer, creating an impact of the surface, attach the silt fencing roll out on the surface, section 1 part at a time. Step 5, the most important part of the process, which is backfill and compaction. These 5 steps are rarely followed on a job site because they're very time consuming and costly. So we as a team are creating a prototype in which we can narrow down the steps to create a more cost-efficient and timely manner process. The problem with silt fencing today is the placement of the fencing, the amount of fencing, the proper materials for the fencing are not being met by human resources standards, which is causing a major environmental issue. Insufficient silt netting allows for water runoff, contaminating our bodies of water. We were inspired to create the silt fencing system when we started talking to professionals in the construction field and speaking to them about the problems with construction sites today and how they could be improved. We're also inspired by our mentor, Dr. Davidson, who informed us of the environmental issue with water runoff from construction sites. We then researched the effects of silt fencing and how they are causing large-scale problems. For the first design, we purchased a contractor-grade silt fencing, no-dig landscaping edging, and a box of panhead screws as seen in Figure 7. Using the product, we were able to put in the 10-foot section of silt fencing to make a model of a typical silt fencing on a construction site. We then secured the garden edging and fencing after we proceeded to stretch the landscaping edging to 10-foot length of the fence. Next, we tucked and placed 12-inch pins every few feet in order to secure the edging to the silt fencing to the ground. Finally, we placed a panhead screw on the opposite side to prevent any movement. The problem with the design, it was not feasible to put around a whole construction site and potentially too costly. For this next design, we used more cost-efficient and productive materials, including PVC lattice and metal T-brackets. Using the 10-foot section of fencing installed from the first design, we created a new support system by cutting the 2 8-foot pieces of PVC lattice down the 5-foot section. The next step was joining the 5-foot sections together with one of the metal T-brackets, as well as securing the remaining brackets with panhead screws. We then tucked the silt netting under the PVC brackets and hammering it to the ground to create a watertight seal. The reason we see this design to be productive is that the T-brackets that are pinned to the soil prevent water from traveling under the fence, also creating control of soil and sediment. This prototype is created by 1/2-inch PVC pipes attached to a 90-degree elbow. The goal for this design is to provide a fence over a hard surface instead of sticking it into the ground. As seen in Figure 11, design is placed on the ground with no attachments needed.
After many hours of research, we have come to the conclusion that the best way to test this prototype is to place it in a real-world situation. As our testing method, we plan to take this prototype on an active project site during the beginning phase of the project. We will then check on the silt fencing frequently, and we will be judging it on the success and failure based on the manufacturing, on-site assembly time, cost efficiency, durability, and weight and strength. We'll make sure that this product is able to be taken down and reused for sustainability purposes. Overall, the silt fence should eliminate the sediment particles from traveling outside the project site. Even with great results from our first 2 prototypes, we're eager to keep improving and finding more ideas on how to be more sustainable. By reducing the amount of waste occurring, we have decided to base our developing model based on all plastic products which are recyclable, which can be reused and refurbished and not go to waste. On these images you see are the images of our developing our model and ideas on the software Onshape as they will be 3D printed. As you can see in Figure 13, we have provided an image of the shaft pipe that will be attached to the silt and used as our main source of stability into the soft surface. In the next figure displayed, Figure 14, which is a connection cap that will be used to attach the 2 shafts together given the prototype firmness. In Figure 15, we have created saw pins that will be connected to the silt netting and driven into the ground between each set of shafts. This is the 3D printing, which helped us visualize our design and turn them into a reality. With having the ability to develop these ideas on Onshape and being able to 3D print them, it played a huge role for our design process because we were able to tailor the models to the exact specifications that are needed rather than going to the stores and search for things that don't work. The process overall helped us to create a stronger and more efficient prototype. In the figure above, we're using PVC pipes to create our prototype. In doing so, we're providing durability and long life to the silt fencing system. Adding on, we're anchoring a 1-inch pipe 3 feet above the ground and 1 foot below ground surface. The pipe will be attached to a wheel that will allow the pipe to rotate clockwise to pull and counterclockwise to release. The idea is to create a semi-pulley system where you can extend or reduce the length of the silt needed for the project. The system will have a handle to crank and the silt will be passing through 2 3/4-inch PVC pipes attached to each other. At the end, we'll also provide an anchor to allow tightening and releasing. On our site visit with Manhattan Construction, we met with the on-site project engineer, Will Pine. He was able to walk us around the site and pointed out that the silt fence on the project site is very important in controlling the sediment flowing downhill. As you see in Figure 22, the sand is piled up against the fence, causing the fence to lean. The sand buried the fence about half a foot above the ground. As Will Pine said in quotes, one time the fence broke and it caused the whole street to flood with mud being on the main road and rain coming down. It was a very stressful day for me to fix it. Overall, the main idea that Will was trying to get across to us is that he's constantly having to deal with silt fencing breaking and causing problems. The final design was successful because we were able to meet all of our requirement criteria. We're able to successfully build a prototype in sufficient manner of time. With anchoring the PVC a foot in the ground, the silt fabric passed through the connecting PVC and attached to the anchor. We're able to tighten and the silt netting. With this being said, we're able to noticeably see the strength of the fencing system. The fencing is prepared to withstand any rainstorm, and it will keep soil sediments from passing through and causing harm to natural water resources. In conclusion, silt fencing is not properly being installed on construction sites, which causes water runoff and contamination to the environment. Many times the silt fencing is just thrown away after a construction project is finished, which is a major waste to the environment. Our prototype is easily installable, reusable, cost-efficient, and durable, which does not allow any water runoff. We would like to thank CUA Department of Civil Engineering, Dr. Davidson, for all their mentorship and helping us out through our design and build process. We'll also like to thank Grace Pauly for her support and feedback throughout this semester. Lastly, we would like to thank all the professionals, especially Manhattan Construction, that allowed us to use their project site and everyone else who inspired us and gave us helpful pointers on how to create a better and more sustainable silt fencing system. Thank you. Thank you.
Thanks, team. This is our last group and our last set of questions for our team. What questions do we have?
Very nicely done. What is the cost estimate for this compared to a regular silt fence? I mean, is it something that commercially you think that's going to be viable?
When I did an example on my report, I did a 200 linear feet project, and the cost came to $247.
That's material installation?
That's just
material.
Just material.
And how does that compare to a regular silt fence?
To be honest, it's just the other silt is the other silt fencing is basically it's made out of like wood, and when it's installed is installed in the excavation process where the excavator digs the ground and then they just place it and then they backfill it. So that's including the excavation cost.
Mm-hmm. And then how many reuses you think you can get from the material?
I think that we would be able to get a lot more reuses than the old silt fencing. We haven't been able to see the process of reusing it, but due to the material of using strictly plastic and silt netting, that it would be more reusable and sustainable than wood breaking, and you'll be able to maybe melt down the plastic and reuse it for future projects.
Very good. Thanks for the answer.
Great. Do we have any other questions? All right, so let's give them a round of applause. Thank you for all of the teams.